more so like conceptual. Yeah. So this is the model that we typically have. So we have log of a I is equal to alpha 0 plus alpha si. I apologize if I change the Greek letter that goes in front of the s's. The interpretation is the same. It's just what is it? Plus beta ai plus epsilon I, where this ai is ability. Right. Now, typically we think about this as being unobserved. Right. But here, what we're going to do is we're going to say this is the true model, right? If we cut observability, this would be the true relationship between years of schooling and ages once we accountability. Now, what we know is, so we know that our OLS estimator of alpha is going to be the covariance of yi, where yi is going to be the log wages, which we typically use, and si over the variance in si. Right? You guys remember this from the homeworks and from all of the lectures and everything like that? This is a relationship that you should remember. This will be your friend number 2. Right? Okay. So if we write this out, so this y has a couple of terms. It has this constant term here. It has this use of schooling. It has this ability, and it has this epsilon I, right? But we know that the covariance operator is a linear operator, meaning that the covariance of y comma a plus b is the same as the covariance of y comma a plus the covariance of y comma b. Right? Everyone remember that? And so we can write this out as covariance of yi alpha 0 plus the covariance of, sorry, let me do this, I apologize. Yi is all of this here, so it should be the covariance of alpha 0 and si, right? The covariance of alpha I the covariance of alpha si comma si. Right? Everyone see this so far? What we're doing? We're just taking each of these individual terms and computing the covariance of each individual term with si. Because each of these individual, the sum of all of these terms is going to be, let me write this out more explicitly. So this is going to be the same as covariance of alpha 0 plus alpha si plus beta I plus epsilon I with si. Everyone sees that, right? This whole term here is just yi. Any questions so far? Is the pace okay? All right. And this is going to be divided by variance of si. So we can split this up into its component terms. So the first term is going to be the covariance of alpha 0 with si. Covariance of alpha 0 with si. Plus the covariance of alpha si with si. Right? So just take this term and compare it with si, and take this term and compare it with si. plus the covariance of theta AI with SI. Right? Plus the covariance of epsilon I SI. Everyone sees this here. We just wrote this out. Who does not follow this? Okay. And then this is divided by the variance of SI. Okay. Now let's observe. So what we've done is we've said that this is the true model. Because traditionally this is unobserved here, and so typically this is the error here. The error is all of this term here. But now we're saying, like, what is the relationship when we have the true model? Right? Okay. Now, the thing to notice is that this alpha 0 here is a constant term. And so its covariance with SI is going to be equal to what? 0. Why is it going to be equal to 0?
If it's constant, then it's not going to change.
That's exactly right. If it's constant, it's not going to change, right? If it's constant, it's always going to be equal to its expected value. It's not a random variable. So it's a covariance. So the covariance of a constant with a random variable is 0. I'll give you a true or false question. So this is going to be 0. Okay. Now this term here, so we have the covariance of alpha SI with alpha with SI. Now when we have a constant like something with the covariance of this, we can just pull out the constant. Right? And so this term here is just going to be equal to gamma times the covariance of SI with itself. Right? This is just going to multiply everything up by that because we can take out a factor of that for the covariance. Okay. Now what's the covariance of SI with itself? Variance of SI. We have the winner. Okay. Now, because we've taken out, in our true model, we've taken out the part of the unobservable that is correlated with the school. We're going to assume that this error here now is not going to be correlated with years of school. It's going to have a 0 covariance with years of school, right? Because when we were running our original model just had alpha 0 plus alpha SI plus epsilon. And so we weren't able to control for ability. And that was the reason why we had an endogeny issue. It was because we had an unobservable that was affecting earnings. And that was affecting earnings, it was also affecting how likely we were to go to school. Does that make sense? But once we put in a control for that, like this covariance here should be equal to 0. That's a subtle point. Does everyone get that? Who does not get that?
Can you explain one more time?
Yeah, sure. So I'll write this out. So we can think about so in our basic model, which we can think of as being like wrong, what we had was log wages is equal to alpha 0 tilde. And I'm going to put these tildes here just to differentiate between the parameters in the model that has a unit variable bias problem, the model that doesn't. Does this make sense? Okay. Plus alpha tilde years of schooling plus epsilon I tilde. Right? And so what's happening, what's the difference between this model number 2 and this model number 1 here is that this error term here actually nests ability. So we have an AI that's buried in here. But because we can't measure AI, when we do our econometrics on equation 2, we're going to be capturing the fact that the epsilon i's has this unobservability. Does that make sense? If it doesn't make sense, that's fine. You can say it doesn't make sense. Okay, it does? Okay, good. All right. But once we account for... No?
No, I got it.
Okay. Once we account for ability, then in a sense, this epsilon I should not covary with the years of schooling. that make sense? Okay, good. So this here should be equal to 0. Right? What we end up from here is that alpha is going to be equal to let me call this alpha hat. This is going to be our estimator here, right? I just put the hat on it because when we do the OLS procedure, this is going to be our best estimator for what the alpha is going to be. And what we're going to do is this is the true value here, and we're going to look at the difference between the true value and the estimated value. Okay. So this alpha hat is going to be equal to alpha times the variance of SI plus theta times the covariance of AI and SI over the variance of SI. Right? And so we can just say that's equal to alpha plus theta times the covariance of AI and SI over the variance of SI. So now we can take this alpha over to this side here. We get alpha hat minus alpha is going to be equal to theta times the covariance of BI SI over the variance of SI. Let's stop here for a minute and ask, what do we do? So if this is our true model, right, but we don't observe this AI, but what we in fact observe is just the SI, then what's going to happen is the difference between the true alpha, so this alpha here is this alpha from our true model, and the alpha that we predict is going to be related to the covariance between the ability and the SI. So if ability and the years of schooling are correlated and they covary, then we're going to get a bias in our estimator.
Let's say that one more time.
Sure.
Or
Sure. So when we look at this very simple model, the way that we get what this alpha tilde is here is we just do what's the covariance of y with SI divided by the variance of SI, right? And if we were to do that procedure, but in fact this is our true model, what we're going to get is we're going to get the true alpha plus some additional term here. And this additional term here is coming through the fact that there's a correlation between ability and years of schooling. Does that make sense? Everyone with me so far? So, in particular, right, let's suppose, I remember what this alpha is saying is, this alpha is telling us, do people with higher ability get more wages or do they get less wages? So for example, if theta rather is positive, then what that's going to tell us is that folks who have higher ability, on average, are going to earn more money, right? Okay. So if we suppose that, and for you guys in the back, can you see down to here? If we suppose that theta is greater than 0, the interpretation is that higher ability people earn higher wages, right? Okay. Now, the question becomes, if the covariance between ability and schooling is positive, what does that mean? If the covariance between ability and schooling is positive, what does that mean? What's the interpretation of that?
Part of the effects of schooling, or part of the effects of ability is captured in the schooling age.
Right, that's right. You're like a step ahead of me.
Okay.
Let's take it back just one step before that, but you're definitely on the right track. If ability and years of schooling are positively correlated or have a positive covariance, what does that tell us about more able people and how much schooling they get relative to less able schooling people? Less able people.
People with higher ability than our school.
Exactly. So this, so what that means is that people with higher ability get more schooling. We also suppose that theta is greater than 0, right? So we can add another sentence, right? That we also know, or let's say assume, that theta is greater than 0, which implies that people with higher ability, what is this? They earn more money, right? And so what do these two statements tell us about the bias if we ran this simple regression where we ignored ability? Is it going to be bias upwards or downwards?
Upwards.
Okay, why is it going to be bias upwards?
Because you're essentially double counting with schooling and ability. So if they're related, because people with higher ability already get more schooling, like that's going to be represented in the schooling. But then you're also counting another variable of ability. So it's like kind of double counting ability.
Right. That's exactly right. Does everyone understand what Tim said? So here's the idea, just to restate what Tim said. So folks who are higher ability are going to earn more money. And people who are higher ability are also more likely to go to school. And so if we don't observe ability, what we will be saying is that, oh, we see folks who are going to college and we think they earn a ton of money. However, these people who go to college tend to be higher ability, and they tend to be higher ability because the covariance between ability and schooling is positive. Moreover, higher ability people, even independently of getting more schooling, would have earned more money as well. And so the bias is going to be upwards. And so we look at this expression here. This is going to be like the estimate. This alpha hat is the same as the alpha tilde here, because it's just the covariance of yi with the years of schooling, which is what our best estimator for alpha tilde would be up here, right? Because remember from class where we looked at a very simple linear model like this, if we only had these two parameters, then the linear parameter would just be the covariance of y with s divided by the variance of s. So this term here is the bias. Right? And this here is positive by assumption, and this is positive by assumption, and so we're going to get an upward bias. So this bias is the estimate for returns schooling upwards. And this was where we wanted to get instruments, right? Because what the instrument is going to do is the instrument is going to be something that's correlated with schooling, but it's going to be uncorrelated with, it's going to be correlated with schooling, but it's going to be uncorrelated with this unobserved ability, right? And what I'm going to do is, so I know that you've already seen some of this before, but I'm just going to give you like a quick shorthand for how we can get around some of these issues. Okay. So if we had an instrument Zi, right? That is correlated with schooling, but uncorrelated with unobserved ability. that implies that we can get an unbiased, estimate of the returns to schooling. Okay. We'll stop there. So the question is, how does this work? So this is our model here, right? So to see this, what we could do is we could say, so as we did previously, we let yi be the log of wages. Right? Let's compute. Let's compute the covariance of yi with zi. Is everybody with me in the notes so far? No? I'll wait for a moment, just so we can write that down. So what we're going to do is we're going to compute the covariance of yi with zi, and we're going to show that we can get an unbiased estimate of the returns to schooling, which in our model here is just going to be alpha without any subscript. Right? And that alpha in particular is going to be the covariance of yi with zi divided by the covariance of xi with zi. That's what we're going to show. And what's powerful about this is you can just show this in 2 or 3 lines. So some of these formulas you don't even need to memorize because you can derive them. Okay. I see a couple of you still writing. And then what we're going to do after we do that is we're going to talk about some of the examples of the instruments that we've seen in the literature. And we'll talk about how you compute coefficients from these instrument variables. Does that make sense? Okay. Everybody has this down so far? Okay, I think we'll just finish right. So if we look at, so the covariance of yi with zi is the same as the covariance of, now yi is going to be alpha 0 plus alpha si plus theta ai, right, plus epsilon I. We're taking the covariance of that with zi. Okay. So what I did was just wrote out yi here. So we're going to take the covariance with zi. Now let's do this element by element, which is the same thing that we did previously. So we do the covariance of alpha 0 with zi. That's the first term we get. The second term that we get is the covariance of alpha si with zi. Right? The third term we get is going to be theta ai with zi. So theta ai, covariance of theta ai with zi. But I'll just wait for a second before I do the last one, so you guys can catch up with the writing. And the last term is going to be the covariance of epsilon I with zi. Okay. What's this first term equal to? The covariance of a constant with our instrument zi. Who thinks it's 5? Who thinks it's 16? What's the covariance of alpha 0 with zi? 0. Okay. What's this term here? How can we simplify this term here? We can take out the alpha and then we get what alpha times what?
Covariance.
The covariance of si and zi. Right? How can we simplify this term here? Say it again.
So you got theta,
We take out the theta and then we get what?
covariance of alpha I Z I.
Covariance of AIZI, right?
Sorry.
The covariance of AIZI, right?
Okay.
Good. And what about this term? What's the covariance of the epsilon I to ZI? What's that give?
Zero.
Zero. Right, and that's going to be equal to zero because our true model says that this is exactly how we explain wages. So there's no other omitted variable that's happening in this epsilon I. The only thing is this ability here. Now, what's the assumption that we made about the relationship between the instrument ZI and ability? That they're uncorrelated. So if they're uncorrelated, what does that mean about this covariance of AI ZI? Zero. It's going to be zero, right? And so there are a couple examples that we saw in the lecture yesterday. There was an example that was for educational attainment. Yeah, geography and quarter of birth. So like distance from college, for example, a quarter of birth. Like there are high ability people and low ability people born in every quarter of birth. It's not like they say, okay, all the smart people are going to be born in January, and all of the slow people are going to be born in some other random month, right? And so this is equal to zero by assumption. This is what makes a good instrument. That's called the exclusion restriction, right? So the exclusion restriction is that the instrument is uncorrelated with the error, and it's uncorrelated with the unobservable stuff, right? The exclusion restriction is that the instrument is uncorrelated, and being uncorrelated is the same thing as having a covariance of zero. It's uncorrelated with the unobservable. Right? And the second thing is called the relevance condition. Which is that this term here better not be equal to zero. Right? Because we need the instrument to be affecting your schooling decisions but uncorrelated with your ability. Right? So the quarter of birth, for example, because there's this dropout rule, if you are 16, you get to drop out. You get to drop out once you're 16, but then like when you start school depends on your quarter of birth. So like if you end up like starting school late, then you're more likely to drop out of school before you're more likely to reach the age of 16 before you complete your schooling, and so you're more likely to drop out of school, right? 2 things. So the relevance condition is that the instrument is correlated with years of schooling. Or whatever the thing is that you're instrumenting for, right? So this is basically saying, that the covariance of SI and CI is not equal to zero, but the covariance of SI and AI is equal to zero. Now let's go back to equation 3 here. So on the left-hand side, we have the covariance of YI and CI. And on the right-hand side, we have alpha times the covariance of SI, CI. Right? Questions about this?
Exclusion restriction? Is it covariance is zero?
Yeah, this is CI. Okay. That was a good catch. So the covariance between CI and ability is equal to zero. Okay. Okay, so looking at equation 3, we can solve for alpha. What is alpha equal to? You can tell me what alpha is equal to on equation 3. What is alpha equal to? This is equation 3. Alpha is equal to what? Say it again?
Alpha is zero.
No. This is equation 3. Solve this for alpha.
Covariance of Y yi, zi minus covariance, or theta covariance.
This is equal to 0,
Huh?
right?
That, setting that equal to 0?
This is equal to 0. Remember we said that the covariance between ability and the instrument should be equal to 0 by something?
Okay,
So we
so
have-
just divide, isn't that just divided by the covariance of SIZI?
Exactly. Does
Yeah.
everyone see that? Because what we have here is the covariance of yi, zi is equal to alpha times the covariance of si, zi. So that implies that alpha is equal to the covariance of yi, zi divided by the covariance of si, zi.
Do you have a darker marker?
Yeah. So we had, can everyone see this better? The covariance of yi, zi is equal to alpha, the covariance of si, zi. That implies that alpha is equal to the covariance of yi, zi divided by covariance of si, zi. We can put a subscript IV here because this is going to be an instrumental variable. And so the key thing to notice here is, let's take a step back. So we have data. The data that we have is, what do we have data on? We have three things that we have data on here. We have, what's that? We have wages. What else do we have? Years of schooling. And what's the third thing?
Ability.
We don't have ability. Ability is not observed, remember? Z, which is the instrument. So for example, like distance to school or quarter of birth or something like that. And we want to know what's the returns to schooling. What is the problem? Why couldn't we just run a regression of wages on years of schooling? What was the problem? Say it again. Admitted variable bias. And why was the admitted variable bias important in this case in particular?
Because you're overestimating schooling on wages.
Exactly. The admitted variable bias was important because we were overestimating the effect of schooling on wages. And why are we overestimating the effect of schooling on wages?
Because schooling was correlated with the error term.
That's right. Schooling was correlated with the error term, which was the observed stability. And so to address this issue, what did we do?
Broke out ability from the error term.
We broke out ability from the error term, and then we did something else too. What's the third piece of data that we have? We have the instrument, right? And how does the instrument help us?
Makes it a unbiased.
Okay, but how does it do that? What is instrument?